Okay, now let's look at the module 2a, secure multi-party computation and the trusted execution environment. As an overview, both MPC and PEE has the same goal. And the goal is to protect the confidentiality of data while we compute queries on top of it in an untrusted setting. So compared with traditional cryptographic techniques like encryption, here, like the goal is that we want to protect the confidentiality while the data is in the change. And over here, like the attack vectors are also different. So first, of course, we want the protection of the data, and that is we want to, for example, have the data encrypted such that the data and all the intermediate result of the data is always kept private. And also, we want to protect like almost all the side channel like leakage. For example, there could be potential leakage from the queries instruction traces and many other different kind of patterns, and we want the security to hold even with such that this kind of leakage is prevented. The greatest challenge in computing with confidentiality is that there's not really anything that we can trust. In particular, the parties with the data may not trust each other for different kind of reasons. For example, they may not have the benign intent, the other party might actually want to get some other people's data. And also, parties may not have the capability to protect even their own machines. So some of the parties may be hacked by the adversary, so that they will be controlled by the hacker. And in this way, we cannot really trust any other party. And the technology for confidentiality computation essentially brings back the trustlessness in some way, so that we can still compute as if there is a trusted party. Regardless of the underlying technology that we want to use, for example, MPC or TEE, we can always view the technology as a trusted party. For example, we have two parties, each with their own private inputs. And in this particular case, some zip code, we have the party on the left with 3 zip code and party on the right with 3 zip code, and they want to do some computation on top of their input. So we could view our technology as a trusted third party. And in this case, once we have a trusted third party, the problem becomes easy, because the parties can just send their input to the trusted party along with the function that they want to compute. And in this particular case, it is the intersection of the set x and y. And then we are going to hope that this trusted party is going to be able to compute the function, the outcome of this function on both parties' input, fx and y. And in this case, the fxy should be the intersection, which is 60201. Okay. However, if this is just the case, then it will be the best, because then we just need to focus on how to instantiate this trusted third party using different kind of technologies. Okay. Unfortunately, the trusted party usually also send back some other information in addition to the computation of the outcome of the function. And this is so-called the side channel side information. Okay, and this side information may not always be desired. Such side information can have a different kind of form. For example, it could be a program trace, which is about how the program counter moves depending on the input. It could be data access pattern. For example, it is about how the program fetches the data from the memory depending on the input. It could be something that is more subtle, like the program execution time or even intermediate result size. And all of them is one way or another could leak some information about the input. Some of them could be less harmful than others, but all of them leaks information in some manner. Okay, and for some of them, we could solve them in a naive way by always just heading to the worst case cost. For example, the program execution time, we could try to make the program run it's always in the worst case time. And for the intermediate result, we could also do something similar, such that the size is always padded to the worst case, so that no information is revealed. However, for others, it could be more subtle, like a program trace and data access patterns. These could be more these are highly non-trivial, and we need to use advanced techniques to hide them in a better way. So in the following, we are going to first focus on data and trace obliviousness for the data and the program. Okay, Let's first take a look at the program trees. Okay, suppose that we, following the previous example, we have X and Y as two input set. X has three elements and Y has three elements. Okay, and let's say could we implement a program that actually compute the intersection of these two sets? Well, we can just run a double loop, right? So let's say we can first check, and in this particular case, we just wanted to just check the size of our intersection. So we first initialize the result to 0, and then we do a double loop. Okay, so we can just enumerate all the elements in the set X, and then enumerate all the value in set Y, and if they are equal, we just increment the result by 1, and then we can just break so that we can continue to the next element in X. Okay, and we can see that actually, if there is an intersection, then if the number of elements in the intersection equals to the number of times that there will be a break, and the timing of the break, it reveals like which element in X and Y matches to each other. And as a result, we can see that actually the program counter, when we execute this program, highly depends on the value of X and Y. So this is the program that is not oblivious in its program trace, because the program trace depends on the input. And the second trace is data access trace or data access pattern. This can also be illustrated using a very simple example of binary search. Okay. So we wanted to search the value val between the boundary at the boundary between S and T. So what we do is that we first calculate the midpoint of the array as the array boundary S and T, and then we want to compare the value and the mem at the middle value. And depending on the result, we are going to either search on the left-hand side and the right-hand side. However, this really depends on the value of mid, and the value of mid depends on S and T. However, if we think about it, the value S and T actually depends on the comparison from the previous recursion. So essentially, like if the value is smaller or equal to, then we are going to go to the left-hand side. Otherwise, we'll go to the right-hand side. So this two argument actually depends on the comparison. So in the end, so what's happening is that this memory of mid actually really depends on the value val, and this is an example where the data access trace actually depends on some private input. So we can see actually this kind of different kind of trace can reveal information in many different kind of manners. And in order for a program to be oblivious, so that is like it doesn't really reveal anything from the trace, we have a formal definition. So in our formal definition, we say that a program is oblivious if for any input I of this program, there is an efficient algorithm S such that the trace when executing this program on top of this input is indistinguishable from the output of this program with this algorithm S with just the information of P. So essentially, this means that whatever revealed by this trace when executing the program on the input can be kind of simulated with some algorithm without the input, but only the program. And if this is the case, then it means that this trace doesn't really contains much information about the input. And the exact definition depends on the trace. For example, the trace can be the program trace, it can be the data access pattern trace, and it can also be any other kind of trace. So now that we know the definition of oblivious algorithms, then we can take a look at some examples. And here we are looking at an example of a more efficient oblivious algorithm for computing the size of the intersection. So in the previous example, we could just not run this break in the program. In that way, if we have two sets, each of size n, then the program is going to run in time n squared. Okay. However, we can actually do better by designing something that runs in time n polylog n. So the way and the program is and the algorithm is not that complicated. Okay. So our first step is just to combine the two sets into one vector z. So this is going to contain the information from both vectors. And after we have this vector, we are just going to set a value result as 0. And after that, we are going to do a trace independent sorting of the vector z. Okay, after this trace independent sorting of z, we are going to get one set such that if the value are the same, then they are going to be located side by side together. And after that, we just need to do a linear scan of the element in the vector. Okay, and if the neighboring value are the same, then we just need to increment the result by 1. Okay, note that now all the accesses to Z are actually deterministic because we're just doing a linear scan. And because of this, the second, this for loop actually does not reveal any information. So we can see that actually the whole algorithm is very cheap. It runs in linear time, except this trace independent sorting. And for this sorting, it could actually be done efficiently in time and polylog n. And one example to do this in a trace independent way is to use this kind of sorting network. And we can see, and every error over here refers to a compare and swap gadget. And after all this number of compare and swap, it can guarantee that all the output is going to be sorted, and regardless of the how the input is ordered. And here, this is just a very simple example on computing the size of the intersection of two sets. And this kind of oblivious algorithms could go very complicated. And more recently, this kind of oblivious algorithms can go, for example, on graph-based computation. There are also oblivious algorithms designed for specific data structures. They designed to utilize like specific parallelism, and there are also more recent works on how to design like our oblivious algorithms for such that they can support more efficient sorting. Okay. On the other hand, another way is to design oblivious algorithms that can support arbitrary RAM access. And once we have this kind of tool, we can design oblivious algorithms more efficient, like much easier because anyway, like the current algorithms that we design runs on the RAM model. So if we have a oblivious RAM, then we can just port existing algorithms to this kind of framework. As a recap, assuming we have a trusted third party, then we can come up with a solution for confidentiality computation. So we just need to have a trusted party and then send our information, send our input and the function to the trusted party. The trusted party is going to send back the outcome and also come with this side information or leakage profile. Okay, and then in order to mitigate this leakage, we can use different kind of techniques. And previously, we already discussed how to hide the program trace and the data access trace. Okay, the program execution size and the intermediate result size can be hidden in many other different kind of ways. And actually, I believe in the follow-up modules, we are going to talk about some of them, how to use differential privacy to hide some of them. Okay, and in the next part, we are going to talk about how to actually instantiate this trusted third party. Our first way to instantiate this trusted third party is to use a cryptographically secure multi-party computation protocol. Multi-party computation is actually a very big topic, and it consists of many different kind of protocols and techniques. And as a way to quickly illustrate the concept, let's first look at a simple protocol. Okay, suppose that we have 9 parties over here, and each of the party has a number. Okay, and the number is only private to themselves. And the goal of all the parties is to compute the sum of all the integers across all the parties. Okay, and we want to design a protocol like this. Okay, and actually, there's a not too complicated solution for this problem. Okay, so the idea is that we could first ask one of the first party to randomly pick a random integer from a very large domain, let's say R. Okay, and then the first party can just send R plus x1 to the second party. Okay, because R is random and very large, R plus x1 is almost uniformly distributed. So it almost does not reveal anything about x1. Okay, and then the second party can accumulate its own input to this to R plus x1. So the second party is going to send R plus x1 plus x2 to the third party. And the third party is going to do something similar and accumulates its own input to this number, and so on, and so on, and so on. And finally, x9 is going to send R plus sum of all the integers to the first party. And at that point, the first party can subtract R and get the sum of x9. Okay, Well, so the first question is why this protocol is secure. Okay, well, this protocol is secure because this random value r is large enough. So so r plus a any number is going to be statistically indistinguishable from a uniform number, uniformly distributed number. And the recap, remember, compared with our previous definition of trusted party, we can actually show that this protocol that is executed among all the parties is as secure as all the parties sending their own input to the trusted party. This is in line. It is in line with the definition previously in terms of the trusted party. Okay. However, this protocol is not exactly as secure as we would hope for. So why that's the case? So let's think about the protocol and see why this protocol could be insecure in some cases. Okay, well, so the protocol is not going to be secure. Let's say, for example, if the first party and the third party collude, and in this case, so the first party send r plus x1, and the third party gets the value r plus x1 plus x2 from the second party. So if the first party and the third party collude, then they can essentially just subtract the value r plus x1 plus x2 and r plus x1 and get x2 out of it. Okay, so we can see that as long as if any of the two parties in this protocol collude, then they will learn some information about a subset of the party's input. And this is obviously not a very not a very good outcome. Okay. And secondly, this protocol could also be broken if, let's say, the first party instead of sending 0, instead of sending r, it can send a 0. And in that case, there's no random padding to protect the privacy of the protocol. Or if any of the party in the middle could, instead of sending the value, it could just send some 0, so that the outcome of the computation is incorrect. Okay. So we can see that actually, although the protocol is secure from some assumption, it may not be secure on the other assumption. So this means that actually, in general, for many multi-party computation protocols, it's very important to understand what is the security model that we are working with. And there are many different kind of classifications depending on the security models. Okay. For example, the first question that we want to ask is how many parties could collude. Okay, and in this case, the popular classifications involves, for example, honest majority and dishonest majority. Honest majority means that out of all the parties, we assume that the majority of the parties are honest and they are not going to collude with each other. Okay, and if there's a dishonest majority, it means that majority of the parties will collude with each other, which is a much harder case. Okay. And the second question we want to ask is about the capabilities of the parties that are not honest. Okay, so let's say if we want to know whether these corrupted parties are semi-honest or malicious. Semi-honest means that these corrupted parties will still follow the protocol, but they are just going to try to collude and learn extra information from the protocol. Okay, for example, in the previous protocol, the third party and the first party learning the information of X2 doesn't really require them to deviate from the protocol. So the protocol, if these two collude, they just need to, a semi-honest adversary will be able to learn X2. And then the second, the notion is called malicious. In the setting of malicious adversaries, the corrupted parties can do arbitrary activities as long as they think that they are viable. Okay, and in particular, for example, if some party actually changes their input, changes the message to something else, let's say 0, then that's a malicious behavior. And the next question we often want to ask is how many parties are guaranteed to obtain the output. Okay, so here we have all different kind of concepts. For example, security with a board, which means that the adversaries may decide what are the parties who may get the output. And the fairness is also fairness and guaranteed output deliveries are also related concepts. In terms of the formal definition of secure multi-party computation protocols, it also uses the key idea of modeling as a trusted party and also having some kind of a simulation involved in the definition. So essentially, So we can view that we have two words. Okay, so in the real world, the two parties are going to execute execute an MPC protocol between the parties, and in the ideal world, the party is actually is going to use a trusted third party. This is what we introduced at the very beginning of this module. Okay, so the security of the MPC says that if there is any adversary that runs in the real world, there exists a corresponding simulation or simulator adversary S, such that from the rest part of the world, these two, the view of these two adversaries are indistinguishable. Okay. So the implication of this kind of definition is that anything that the adversary can be done or could have learned in the real world could also be done or have been learned in the ideal world. And in the ideal world, the adversary cannot really do anything beyond just send the data to the trusted party and get back the outcome and also potentially some leakage profile. So this also means that the MPC protocol actually satisfies this kind of trusted party paradigm. So common building blocks of secure computation protocols there are many different kind of common building blocks to construct efficient secure computation protocols. The basic building blocks include, for example, the Gabor circuit, the oblivious transfer, Beaver triple, and secret sharing. This can be used to build many different kind of protocols in the two-party and multi-party setting. More recent and more complicated tools include, for example, private set intersection, function secret sharing, RAM-based secure computation. They are specialized in certain functionality, but they can be much efficient than just using basic building blocks to build certain functionalities. There are also similar building blocks that could be helpful to construct efficient secure computation protocols, including, for example, private information retrieval for the homomorphic encryption and zero knowledge proofs. Okay. So private information retrieval is a protocol where the client wants to retrieve as a particular block out of many blocks from the server. Okay, so the content of all the blocks are public, but the client does not want to reveal which block is being retrieved from the server. So the server only knows that one block is retrieved, but the server does not know which block is retrieved. That's private information retrieval. Fully homomorphic encryption is a special kind of encryption scheme where we can compute manipulate on the ciphertext such that the underlying plain text can be computed without decryption. Okay. Zero knowledge proof is also is another cryptographic protocol where we can prove things about we can prove the fact about some knowledge without revealing the knowledge. Okay. All of them can be helpful in accelerating and multi-party computation. For example, zero knowledge proofs can be helpful in designing, for example, maliciously secure protocols. Fully homomorphic encryption can be used to reduce the communication overhead of two-party and multi-party computation protocols. While private information retrieval has been very useful to even retrieve some data from a large array of data inside of secure computation. Okay, so because of the time constraint, over here I can only give a very high-level introduction of secure computation. And the more information, there are many other materials, and many of them has been summarized in this very awesome GitHub repo. So I want to just highlight some important key points. Okay, and for let's say if you want to know more about MPC, I think the best source of to learn them is probably through this. BIO Winter School, the first one and the fifth one. This two sets of video lectures actually covers a broad set of cryptographic techniques. And the first BIO Winter School is 10 years ago. So the content has already been very classical, and many of them has been implemented in many ways. The GitHub repo also contains a list of existing implementations, open source implementations that you can use. I just want to point out here that in order to choose the open source library that they want to use, you should first think about how many parties are there that you want to use MPC on top of it. What's the security model, whether it is semi-honest or malicious? and what kind of program language you want to hook up with, whether it is Rust or it's Java or it's C++. This kind of decision you should could always impact the choice of the library that I want to use.
Okay, so now we're going to talk about trusted execution environments. So this is a second technology with which we can compute over private data. We also call these TEs, or secure enclaves, and they use specialized hardware to protect the privacy of database operations. So trusted execution environments are broadly defined as a set of hardware and software components providing necessary facilities to support secure applications. Informally, we're delegating our DVMS's confidentiality guarantees for our data to trusted hardware with a supporting software stack, instead of jointly computing amongst mutually distrustful parties in secure multi-party computation. This execution environment runs in parallel to the machine's operating system and hypervisor. We may use this for databases in the entrusted cloud, where we outsource our data storage and query evaluation there, or for private data federations. This trusted hardware is initialized at boot time, and its administrative control is isolated from the remote system in which it resides. For the user launching their enclave on the entrusted cloud, they don't need any administrative or kernel level access in order to run within the host system. So the confidentiality guarantee of the enclave means that the enclave alone has the key with which to decrypt the database's private data, and then data may only be accessed by the code running within the enclave. So it does this with a web of trust model for provisioning secrets to protect the data and code. So each time we encrypt the data, we use a key that's derived from a root of trust that is a private key etched into the chip for our trusted execution environment at manufacture time. Now, TEs also guarantee the integrity of their query evaluation. When we send data to an enclave, we are proving that we are sending it to this secure environment and that this environment is exclusively running our code with no additional snoops. We also verify that the initial data it starts with is intact and not tampered with by the host operating system. In addition, TEs use secure remote communication to communicate with the end user, as well as amongst themselves for distributed secure query processing. So to motivate this here, let's consider a couple of use cases for this technology. So many of us already use secure enclaves in our workflows. For example, programmable enclaves are used in smartphones to authenticate fingerprints and other biometrics. This makes it so that the system software, including the kernel, if it is compromised, can't be used to falsely authenticate by unlocking the phone or authorizing purchases. And these systems can become quite sophisticated. So for example, Apple manufactures one for its devices that with a system on chip, and it has a fully programmable system, including a boot ROM to establish this root of trust, an AES engine for efficient and secure cryptographic operations, Apple's true random number generator, and a section of protected memory. But more importantly for us as database researchers, enclaves are seeing use for computing on an untrusted platform such as the cloud. Here, we want to delegate our storage and query workloads to an untrusted third party, such as AWS or Microsoft Azure. But we don't want to disclose our private records to the cloud vendor. Shown below is an example of an overview of how Microsoft SQL Server uses the Azure Confidential Cloud Computing Platform in its query evaluation. So you can see here that from the user's perspective, they submit a plain text query, and the API remains roughly the same as it was before. But now the SQL client driver will encrypt the query and send it as ciphertext over to the engine, where the enclave alone has the ability to decrypt the ciphertext and also decrypt the input data, run the query, and produce the results and send them back to the user, where their client driver will decrypt the answer and return it to the client. So here, we're really saying that the system has delegated its query processing to this secure enclave, and this protects the database from unauthorized users, including DBAs, cloud admins, and computer admins on the site to which we're delegating. These individuals may have access to the hosting machine, but not to some or all of the data that we are storing. Under the hood, SQL Server is using Intel SGX for this always encrypted feature. So now these trusted execution environments are moving into the enterprise. As this happens, service providers need a solution that protects private records from data breaches and offers regulatory compliance in some contexts. There are numerous initiatives on this front, ranging from commercial products that have widespread adoption, such as Intel SGX, to open source, more experimental enclaves, like the Keystone Enclave project. And this one is based on the RISC-V architecture. There's also low-powered offerings like the ARM Trust Zone and the aforementioned Apple Enclave. So there's a lot of room in here for research in the DV communities at multiple levels of the stack. So as we will see shortly, these enclaves are not able to scale to running a whole application like a DVMS in one of them, owing to limitations in memory size and computing power. So we typically partition our application logic into trusted and untrusted domains and use the enclave for the former, as shown in this slide. Here, the DVMS runs its private code and encrypts its data in this trusted space to which the host system does not have access. Now, an enclave still may access data on the host system if the user calling the enclave code has permissions to do so. But determining what parts of the DVMS must be implemented in enclave is an important part of this design process. Figuring out when are we touching this data, and what other information are we not willing to leak to the cloud providers, such as perhaps the contents of our query or details of how we run them. At a high level, the enclave is offering the programmer two functionalities. First, we load the data and code in order to launch an enclave. This creates an enclave instance with a unique identifier and a proof or signature verifying that the secure instance has launched with the given code that we put forth, as well as the initial data that we provided to it. And that it's running on this one particular TE or chips. We also leverage features of the hardware itself when we're signing it. The second thing it offers is when we execute, when we invoke a function or a program. And here we call the enclave with its unique identifier, and we provide inputs to the program. It produces the output, and it also provides the user with a proof that demonstrates cryptographically that our output was derived from the input program and the initial stored data. So that's how we uphold our integrity guarantee. In addition, though, and this is something where our applications can get challenging, is that TEs are vulnerable to side channel leakage. So we touched on this briefly earlier in the previous section, but recall that an adversary can passively observe IOs in and out of the enclave, network transmissions, runtime, and other characteristics of the query's evaluation, and deduce unauthorized information about the private data or query. So we can't simply port existing DVMS code to an enclave without first hardening it to this class of attacks by making our code's execution data independent. So that's the oblivious feature that we were hearing about in the previous section. So making code fully oblivious is incredibly expensive in terms of performance. Like, we're talking multiple orders of magnitude slowdown if we want to make it so that our database execution truly leaks no information, because effectively we're running in worst case time. So, and that's what we're doing with secure multi-party computation. So we have to make informed trade-offs between full oblivious and running standard code in the enclave, depending upon what types of information we're willing to leak from our DVMS. So the key features that we're getting here are, first, confidentiality for both our code and data. So here we want to protect the confidentiality of private data with an end-to-end approach. So you can think of this as almost like running your DVMS within a virtual machine, albeit a very small one. The data is encrypted at rest, and the enclave alone has the key with which to decrypt it. Recall that the key is based on this root of trust established by the TE using a private key etched into the chip. Similarly, the code may remain unknown to the host OS and to any observers because we can input it in an encrypted form to the TE at lunchtime. Once we create an enclave, the code and the data remain sealed in it. They're not accessible by the rest of the system. Hence, the hypervisor and the OS still can't read them. Second, a user needs remote access to the TE, and they do so by setting up an encrypted communication channel between the enclave and themselves. So here again, the TE has to prove that it is legitimately this piece of hardware, and it has to establish this secure channel between the user and itself. So in addition to connecting with the client or the user, the enclave can also initialize and maintain a secure and verified connection with other enclaves for distributed or parallel query processing. With this, we can maintain our guarantees even when our workload spans multiple machines. So our last main guarantee here is that the enclave will have integrity for the data and the code it runs. It also guarantees that the data has not been altered when we page it in from disk. And to do this, the enclave uses measurements to prove to the user that it is running the correct code and that that code is running on the prescribed hardware and that the data is what we expect it to be. So when we do this in a distributed setting, we're using a similar proof algorithm. Okay, so how do we make this happen? What are the building blocks that we need here? So the first one, in order to do this initialization and launch process for our enclave instance, is remote attestation. So here, we want to verify that we are running on this enclave on this untrusted host. So this is how we provision our enclave. And we generate a set of keys and do a handshake with the user and with at least in the case of Intel SGX, with Intel in order to verify that the code, the hardware keys, and the data are as the user expects. And it does so with this unforgeable signature for the enclave, so you can't forge it. The enclave usually communicates with the user and or the OEM vendor for this process, and the enclave must pass attestation before it can start to run the code. So we have to prove that we are running in the enclave with only the code that we expected and with the data that we need. So second, we have this protected, our second big ingredient is we have this protected memory region for the enclave's data. In Intel SGX, this is called the encrypted page cache. And this is where we can decrypt the contents, the private pages, in a way such that the host OS can't read them. Unfortunately, these page caches tend to be small. And we're talking about SGX because this is the most common one, and it's on about 128 megabytes. But its actual working space can be much smaller. And we'll talk about that more in a moment. So third, these systems come with a set of instruction set extensions. And with those, we can create, enter, and exit the enclave. We also invoke these instructions when we're verifying that we're running on trusted hardware for remote attestation. And when we're setting up trusted encrypted channels with the end user or other enclaves. When we're building a DVMS over TEs, we need to integrate these system calls into the private sections of our application logic. Okay, so with these building blocks, what are some of the design decisions we have to make when we're building this on a trusted execution environment? So if we're building a DVMS. So the first big thing we have to do is we have to define the security guarantees for the system. So in this process, we need to think about our threat models. So we have to say, even though we know that the TE will protect against malicious actors, even on the host operating system, it still remains vulnerable to all these side channel attacks. So you have to spell out exactly what we're protecting and to what extent, like how strong our adversary is. We also need to describe who is permitted to learn what about the data, because that will inform how we protect the side channels, like I/O, memory access patterns, and network transmissions. And then we also have to think about how are we going to manage our IOs, our inputs and outputs? So recall that Intel SGX has about 128 megabytes of memory, but once you've loaded up your trusted code base, the code that you're going to run and the supporting libraries, effectively you have about 90 megabytes to work with at a shot. And so we need to partition the DVMS's facilities into small enclave-sized pieces, and that we have to use the same principles when we're paging data into and out of the DVMS. So One useful way to think about this is by starting about it in terms of query execution. What can an attacker learn? By observing the runtime of the query, cardinality of the intermediate results, by looking at when are we paging things into and out of the EPC or our protected memory. But that's not all, because we have to think about this in terms of the larger systems. We have to say, well, is information being leaked by logging if we're doing logging for recovery? What about if we want to do index lookups? Does that reveal certain things about the underlying data, especially if the adversary knows the query that we're running? Things like managing the buffer pool and so on. So we have to take a more holistic view to our database's design when we're thinking about this in the context of TEs. So our threat model will also, of course, inform what modules in the DBMS must be performed in the enclave. So we have to think both about what subsets of the code need to be run securely. And we also have to think about how are we going to bring data in and out of the enclave in a way that doesn't inadvertently reveal information about the data. So if we're doing things like point lookups and the adversary can see exactly which pages we're bringing in every time, then this is bad. This can leak information about like how many users, like if we're looking at a list of users for a student enrollment system, then we could say, well, now we see that user ID X is enrolled in X classes if we look at how many pages we're bringing in from memory. There's a few common pitfalls that we might encounter while doing this. And this list is not exhaustive. So the first thing is IOs. In a disk-based DBMS, serializing data into and out of the enclave is expensive. And we have a very similar performance pitfall here, where we could, when we partition our data into a format that offers efficient lookups, we have to weigh this against the cost of serializing the data, bringing it in, bringing it out. We don't want to do that repeatedly if we don't have to. But at the same time, we don't want to leak unauthorized information by doing a lot of very specific lookups. And there are some solutions like there's an oblivious RAM for TEs called Zero Trace that can help with this, which brings us down from having to do like an exhaustive scan over the data when we're looking up specific values. We don't want to leak information to, say, a polylogarithmic runtime. But we may benefit from novel data structures here for indexing and lookups. And there's been some preliminary work on this with oblivdb. A second challenge here is that there's really no systematic way to partition a program's native and enclave code to make really strong guarantees. We're basically doing this by hand right now. So when we do this, we have to verify the entire query lifecycle to identify potential flaws in our workload. And this can be really tricky when we have many moving parts together, like logging and index maintenance, transaction or concurrency control, and so on, right? Also, this is kind of an aside, there are some interesting privacy performance trade-offs that we can make when we're designing a DBMS in this setting, meaning that sometimes we may strategically leak some information in exchange for faster query runtimes. For example, we can make our queries run faster if we reveal information about our query results as we go along, such as intermediate result sizes. Or if we're in a distributed setting, we might choose to use non-oblivious shuffle algorithms for things like joining and aggregates. But on the other hand, quantifying the impact or security and privacy loss associated with these design choices is something that we don't really know how to do yet. We can do it in the context of differential privacy, but in the general case, it's much harder. And it's not clear that there even exists a solution for understanding the security implications of these privacy performance trade-offs. So here's a few example questions that we could use when we're designing a DBMS for TEs. One, we can ask, are the queries themselves private? So is the host OS allowed to learn what queries we're running? We can again ask about whether we should protect the cardinalities of intermediate results. So here you can see if we're fully oblivious, then the intermediate result cardinalities can really blow up fast because we have to effectively run in worst case. So you can see here just with a simple join that it has an output size that's equal to the Cartesian product of the input size. And that's clearly not going to scale over a set of joins, right? So another question is, how do we make swapping data in and out of the protected memory data independent? How do we not inadvertently leak information when we're paging in data from disk? And there's a lot of design room here, in my opinion, for access path selection. So thinking like we may find more ways to bring data in. That doesn't mean we have to scan the whole relation every time. So another thing that just to touch on briefly is that TEUs have vulnerabilities. So like all systems, they're susceptible to cycles of finding new attacks, patching them, and then beginning the process again. The side channel problem really can come up because it means that people have been spending a lot of time in the security community analyzing this problem. So here, attackers may try to reverse engineer data access patterns by forcing the enclave to swap in and out of memory. They may also try to exploit speculative execution, like SGX's foreshadow, to extract the enclave secrets, i.e. its decryption keys. But the thing that makes this problematic is that sometimes we can't patch it with software. Sometimes, like for example, with foreshadow, we have to patch this in physical hardware, and that means that updating it can be very costly and time intensive. But so even though we may not have entirely figured out this hybrid hardware system security yet, this is still a valuable platform with which to do research, and it will continue to get better with time. So briefly, there's been a fair amount of work on this topic of DBMSs on TEs. And this really started with Opaque in 2017. And here, this was for select project join aggregate queries, and it supports only read-only OLAP workloads. OblibDB extended this line of work. They added a simple oblivious index structure, and they started to support writes. And there's been work also with EnclaveDB, which is more of a full stack solution. So they offer stronger performance on transactional workloads and built-in checks for the integrity and freshness of recovery logs and of the DB itself. StealthDB is also an interesting work because they sit atop of Postgres, so they really tried to implement this in the context of an existing system, and they investigate a few security models and design trade-offs for performance. But the main thing to bear in mind here is that DBMSs on these trust execution environments have a wide range of decision space options, and in terms of both the workloads they serve and the level of confidentiality and integrity guarantees they can offer. And there may still be fertile ground here for additional research for workloads like HTAP and improving the performance of current systems. So to briefly summarize, in contrast to secure multi-party computation, the TEs are much more efficient for performance. And they also naturally parallelize in a way that secure multi-party computation cannot, because they compute locally instead of evaluating these garbled circuits by passing encrypted messages around the network. So then with MPC, the network can become the bottleneck, and TEs will parallelize more nicely. Now, the cons are that you have vendor lock-in. So for example, with Intel SGX, if you want to do remote attestation, you have to go through Intel. So that means you have to trust Intel. They're also vulnerable to side channel leakage. And that sometimes these security guarantees can be brittle because hardware fixes are slow to roll out. And with that, I thank you.